Okay, welcome to this presentation on video latency. Putting latency to the test. Let me start briefly by introducing myself. My name is Jeroen Caeyers from Wavepart, and I do training consultancy and pre-sale support for manufacturers and system integrators. And my areas of expertise are video, HDMI, SDI, HDBaseT, and IP and AV over IP. The reason I started doing latency measurements is this claim from the SDVoE Alliance stating that their latency is supposed to be less than 100 microseconds. And this is really an extremely low value, and I wanted to know if it's possible to measure this. So the way you usually measure latency on HDMI signals is by using an oscilloscope. But an oscilloscope that can handle the high HDMI data rates is quite expensive. It's the price of an exclusive sports car. So I'm not going to use that. I can afford that, but I am going to use two displays. Ideally they would be identical, but in this case there are two different displays. My phone and an oscilloscope, but this one on the right side is a very cheap one. It's only something like 300 euros. And last but not least, I'm going to use a secret element that I'm going to reveal later on. Let me say something about SDVoE. SDVoE is a 10 gigabit Ethernet solution. It means that you can do uncompressed video up to 4K 30, and uncompressed means very little latency. Because it's a 10 gig pipe, you cannot go uncompressed 4K 60 444 because it's something like 18 gigabits, so you need a very light compression, 1.3 to 1. The nice thing about SDVoE is that it's interoperable, so an encoder from manufacturer A will work together with a decoder from manufacturer B. And there are two basic modes in SDVoE. One is the Genlock mode, and the second is the seamless switching mode. And I'm going to talk about these two modes later on because they give different latency readings. The equipment I used is encoders and decoders from Aurora Multimedia, US-based company. It has an SDVoE chip in it. It's an older version. The IPXTC1, but in terms of latency it's identical to all the new SDVoE products. It has power over Ethernet, and this is a version that doesn't have video wall and multi-viewer, but more expensive versions have this feature. To connect the encoder and decoder, I use a switch from Netgear, the M4300. It's a 10 gigabit switch with copper and fiber ports. And the nice thing about this switch is that it's SDVoE pre-configured. So it works out of the box. You take the switch out of the box, plug in your encoders, decoders, and you're good to go. So it's very, very easy. There are lots of versions available, different number of ports, fiber, copper, and a new M4500 is available, which supports up to 100 gig Ethernet. Back to latency facts. When you measure video latency, you can express this value as an absolute value, something like 10 milliseconds, 20 milliseconds, or you can express it as the number of frames. And if we talk about the number of frames, one frame at 60 frames per second is 16.7 milliseconds. So if you have something like 70 milliseconds of latency, we say we have one frame of latency. Sources of latency in an AV over IP systems. There are four main sources of latency. We have the Ethernet switch, which introduces latency. We have the cabling, video processing, and compression. I can tell you now that the first two are not important because the latency is very low. An Ethernet switch adds something like a few microseconds of latency to the whole system. Cabling signals, whether they're photons or electrons going over the cable almost at the speed of light. So the latency you get from that, they are nanoseconds, so 1,000 times less than a microsecond. What is important is video processing and compression. How much latency is tolerable in a system? Well, this depends completely on the application. If you have a surgeon looking at a monitor doing an operation, it's very important to have a low latency. But if you have a digital signage application, you don't care. Okay, we're going to the first mode, the SDVoE Genlock mode, and I'm going to explain how that works. What we have here on the left is a laptop, on the right we have a display. In between an SDVoE system with an encoder, decoder and switch in between. And in the Genlock mode, the input of the HDMI encoder, the HDMI input, is locked to the output of the SDVoE decoder, which means that they are running the same pace. It doesn't mean that there's no latency. There can be latency. As a matter of fact, there is latency between the two, but this latency value is a constant, yeah, because they are locked, the input of the encoder and the output of the decoder. Before I measure the latency in Genlock mode, I do a reference measurement. What I did is I created a video clip where each frame is a different color. So when I play this clip on my laptop, you'll see fast flashing colors on the screen. So the output of the laptop is going to a splitter, and the splitter is going to the two displays. So they will both show the flashing colors. So when I look at it, I will just see fast flashing colors. I can tell what's going on. But what I do is I take a video of the two displays flashing with my phone, and my phone has a function called super slow-mo. And most phones today have this function. You can make a very nice slow motion with your phone. And my phone, it's a Galaxy S10, does 960 frames per second, which means that for each frame in the flashing video, the 60 frames per second video, I have 16 frames in my super slow-mo. So I can really see what's going on the two displays. Let's look at the result. This is a video. You will first see what's going on in real time, the fast flashing colors, and then it goes over to slow motion, and we can see what's actually going on. So what you see here is actually the refresh of the LCD panel inside the displays. Yeah, so the screen is refreshed from top to bottom. And what you see is that they are perfectly aligned. Yeah, so there's no latency between the two, and of course it's a reference measurement. So that's very nice. I have my reference set now. Now we are going to do the same thing, same setup. The only difference is that at the bottom there is an SDVoE system. So the top side is the reference, the bottom side is the SDVoE system. I'm going to do exactly the same thing with my phone, taking a super slow-mo, only this time one reference monitor and the other SDVoE. Let's look at the result. As you can see, there's no difference. Yeah, so you can say the latency is 0, stop there and go to work. But that's not what I did, because I wanted to know exactly how much latency there was. So I thought of a way to measure this more accurately. And here is where my secret element comes in. It's an adapter from HDMI to VGA. If I want to measure HDMI signals on an oscilloscope, I need this very expensive oscilloscope, which I can afford. But if I measure analog VGA signals, I can use a very cheap oscilloscope. So on a VGA connector you have 5 main components: red, green, blue, horizontal and vertical sync. And what I'm interested in now is pin 14, which is the vertical sync. What's the vertical sync? There's my video, the flashing colors, and on pin 14, the vertical sync, you will see pulses each time when a new frame starts. Yeah, just like I show here on the slide. So when I see these two pulse lines on my oscilloscope, I can see if there's a difference between the two in time, and that's my latency. So this is the setup, exactly the same as before. The only thing changed is that I removed the displays and replaced them by converters from HDMI to VGA and connected the VGA to my oscilloscope, both reference and SDVoE system. Yeah, and now we're gonna look at the latency between the two. So here's my video on the real life setup. We had the switch on the left, we have the encoders and decoders. Here's the management platform on the laptop that's controlling the encoders and decoders. This is my splitter, my HDMI splitter, with the adapter and the probes going to the oscilloscope. This was the reference probe, and this is the probe that's coming from the output of the decoder. And the camera is swinging to the right now, and then we will see the oscilloscope measurement. We will see the sync pulses, both of reference and SDVoE system, and they look exactly aligned. But when I zoom in on the oscilloscope, you will see that there's a difference between the two. And that's exactly the latency that we are looking for. Here's a screenshot of the oscilloscope measurement with the exact same pulses. And on the bottom right side, you will see that I measured a latency of 40.2 microseconds. 41.8 microseconds, about 42 microseconds. And if you convert that to frames, you get something like 1/400th of a frame. So this is really extremely low value. Then we're going to the second mode, the seamless switching mode. Let me explain how that works. Here we have two encoders and one decoder. And what we can do is we can switch the decoder to the different encoders. Yeah, so we can switch sources. In this mode, the output of the decoder is no longer locked to the inputs of the encoders. Yeah, and this is done because we can do seamless switching, as the seamless switching mode says. So the display on the right side will get an uninterrupted HDMI stream. As a matter of fact, the display is not aware that there's switching going on, right? Because it gets a constant HDMI stream. This works great. The only price we have to pay is latency. There has to be a frame buffer in the decoder that buffers a frame of a video to be able to do this. So let's see if we can measure that as well. So what I did first is set up the system the same as before, only this time in seamless switching mode, and capture this with my phone in slow-mo mode. And this is the result. You can clearly see that they're not aligned anymore. So we have definitely increased latency. Yeah, but still it's kind of hard to say how many latency there is. And we have a problem if we start measuring the vertical sync pulses, because all the vertical sync pulses are identical. So let's say that I measure half a frame of latency. It could be that there's indeed half a frame of latency, but it could be 1.5, 2.5, 3.5. I don't know, because all pulses are exactly the same. To overcome this problem, I created a video that's completely black, with only one frame of red in the middle. Again, I used the adapters from HDMI to VGA, but this time we're going to measure pin 1, the red information on the VGA connector. And what we will see on the oscilloscope is a low signal on the red pin, low until the red frame arrives, then it gets high, and then low again. So we have one single pulse for both reference and SDVoE. So we should be able to measure the latency without any problem. Here's the result. Actually, I have two results because the input and the output are no longer locked. We get different latency measurements because the latency is drifting. And these are the two extreme values. This is the lowest latency. You see 17 milliseconds of latency. That's about one frame. And this is the highest latency, that's 33 milliseconds. That's about 2 frames of latency. So the latency is drifting between 1 and 2 frames in the seamless switching mode, which is still pretty low. I would say that in 90% of all applications, it worked perfectly. Yeah, the only when you're talking about the surgeon I talked about who's doing an operation looking at a display, I would go for the Genlock mode instead of seamless switching mode. But in most cases, this will do fine. So the summary, video latency measurements in general, you can get pretty good estimates with your phone. If you have a phone with slow-mo mode, try it out. You will definitely see an approximation of the latency. But better results with these adapters, HDMI to VGA adapters. They're very cheap. If you have an oscilloscope, try it out. SDVoE, in Genlock mode, I measured 42 microseconds. And they advertise a latency of less than 100 microseconds, so that's okay. And it is extremely low, something like 1/400th of a frame. And in seamless switching mode, we have a latency that drifts between 1 and 2 frames. And the drifting is as expected because the inputs and outputs are no longer locked. That's it. Any questions? If you want, you can come over and talk to me afterwards. Thank you very much.